Hello class, this is Brian and company. Are you ready for a fantastic adventure into the wacky world of quantum physics?
Today we are going to be teaching you about a field of quantum mechanics called quantum entanglement.
Quantum entanglement is a very compelling phenomenon. It explains how particles interact to a certain extent in which they are considered identical.
To begin, our universe is made of tiny particles. These particles are called atoms, and there's even smaller ones called subatomic particles. How these particles interact and the study of how they interact is called quantum physics.
The birth of quantum physics is attributed to Max Planck's 1900 paper on blackbody radiation experiment. Development on the field of quantum physics was done mostly by Max Planck, Albert Einstein, Niels Bohr, and Werner Heisenberg, and then Erwin Schrödinger. Ironically, Einstein had serious theoretical issues with quantum physics and tried for many years to disprove or modify it. The three revolutionary principles of quantum physics are quantized properties, properties of light, and waves of matter.
This is when two particles become connected in a way that not even the world's leading quantum physicists can quite understand at this point. When these particles are connected, or as it's officially called, entangled, many of their properties are correlated with each other.
Yes, Alexis. So, for example, the sum of the spin of the particles is always zero.
At the quantum level, particles are so small that the concept of spin means something different than our idea of objects rotating. Quantum spin is a property of a particle that refers to how it interacts with electromagnetic forces. Spin is one of the two components that make up angular momentum at the subatomic level. The other part being orbital angular momentum. While these particles do not actually spin, treating them as if they do is a very analogous way of understanding them.
Since spin is a property that connects entangled particles, if we know the properties of one particle, we can find the properties of another, no matter the distance apart.
Let's say two photons are emitted from the same particle with zero angular momentum. As mentioned before, the spin of these two particles must add up to zero. So if someone snags one of the photons and measures its spin to be +1, then we'll instantly know that the spin of the other photon is -1. These particles shown are entangled because they are in theory emitted from the same source. They're separated by a distance d. This could be a large distance or a small distance. Alexis and Niku are demonstrating how when she measures the spin of particle A, the state of particle B will immediately correlate with particle A.
Whether or not this can be used for instantaneous communication is still being researched. One idea is to measure particle A in a way that forces it to be in a specific state. That way we can also control the state of particle B. But currently there are no methods of doing this that don't break the entanglement between the two particles. So there is still no way to be faster than light's communication. However, this could change in the future as quantum entanglement continues to be researched.
Quantum entanglement allows for information to travel faster than the speed of light. But this does not conflict with Einstein's theory of relativity because the information is not being carried by an object with mass or energy.
According to research by Professor Huan Yan and colleagues at the University of Science and Technology of China in Shanghai, the lower limit to the speed associated with entanglement dynamics or spooky action at a distance is at least 10,000 times faster than the speed of light in a vacuum. This basically means the speed of quantum entanglement is considered faster than the speed of light against the common understanding.
The EPR paradox created by Einstein says that the only way to explain the effects of quantum entanglement is to assume the universe is non-local. Non-locality in this case means the things happening to entangled objects are linked even when the actions can't communicate through space-time. This paradox leads to further understanding of how strange entanglement is.
Quantum entanglement is currently being used in many emerging technologies. However, with so much uncertainty, there are many theoretical uses for quantum entanglement. But most of these ideas are far-fetched and far from being seen in the real world.
Here, Alexis starts spinning her pencil in class during the test because she doesn't know how to answer the free response question. Across from her, Niku, at the exact same time, starts spinning his pencil in the opposite direction at the same speed.
Would you look at that? Our pencils are acted simultaneously.
That blows my mind.
They look at each other and conclude that the two pencils are entangled. So before we move on talking about quantum mechanics, we should first talk about the Schrödinger equation. Now this is the base equation for all of quantum mechanics. It's essentially the F equals ma of quantum physics. The goal of the Schrödinger equation is to find the state of the particle. What the state of the particle is a vector that gives us all the information we have about said particle. So let's break this down. First, we have these two symbols. These represent the state of the particle, as I said before. So I'll put a little label there. So this gives us all the information that we want about the particle and all the information we can get. Now what's interesting about the state of the particle is that at the quantum level, we can only find probabilities for each given state. So what this function really does is it tells us what are all of the probabilities of every given state of the particle. At the quantum level, we can't determine an exact state without taking an actual measurement. So next we'll move on here. These are our universal constants. This first one is I, which is the square root of -1. And this you probably learned about in Algebra 2. It's the base complex number. This is called h bar, which is one of the main fundamental constants of quantum mechanics. It's also known as Planck's constant. So these are our constants. Next we'll move on to this symbol, which is our derivative, as many of you may recognize from calc. For those of you that aren't in calc, what this is essentially saying is it's the change with respect to time. In this case, the derivative is being applied to the state, so this is the change in the state with respect to time. So this is change in state. Finally, we have what's called the Hamiltonian operator. And what this is it's an operator that takes in the state of the particle and accounts for the total energy in the system. So this is the total energy. So what the whole equation is telling us is that these constants times the derivative of the state with respect to time is equal to the total energy operator of the system. And by quantum mechanics can use this equation to solve for the state and can find the probability of any given state for a
Quantum entanglement is a fascinating subject that is yet to be fully understood.
We hope you learned a lot from this video and are inspired to learn more about quantum entanglement and quantum mechanics on your own.
Thanks for watching!